Welcome to the Deep Dive, presented by Knowledge Flow. Today we're taking a journey into a world that, well, it underpins nearly every single digital interaction you have. Have you ever typed a line of code or maybe just clicked to run a program and wondered, what really happens behind the scenes? How do those instructions actually come to life? It's far more intricate and fascinating than you might imagine. We're going to explore the core processes, the steps that transform your human-readable commands into actions a machine can actually understand. And we'll be focusing on the fundamental principles of compiler design. Okay, let's unpack this.
It's absolutely foundational. Understanding compilers isn't just like a niche technical detail. It's really about revealing these hidden layers of logic that make, pretty much all software possible. This exploration, I think, will offer a really unique perspective. It gives you insights into how these, frankly, complex systems turn intricate details into genuine aha moments. Hopefully it'll give you a better grasp of the digital world all around us.
Okay, so let's start with the most fundamental question then. What exactly is a compiler?
Right. Well, at its core, it's a specialized kind of program. Its main job is to read a program written in one language.
Usually something high-level, human-friendly.
Exactly, like Python or C++, something we can easily read and write. And it translates that into another language, typically a much lower level language, something closer to what a computer's processor can execute directly.
Okay, so it's a translator, but you mentioned it's more than that.
Oh, definitely. It also acts like a really vigilant proofreader. It flags errors it finds in the original program, syntax mistakes, things like that. So it's really an essential tool. It helps create a much more efficient and supportive environment for developing software.
That makes sense. The proofreading part sounds crucial.
It is. And the why behind this translation is critical. We, as humans, we think and write in these high-level languages, right? They're full of abstractions, readable syntax. But computers, they only understand machine code, pure binary instructions, streams of ones and zeros. Compilers are the bridge across that fundamental gap. And their role, it really goes beyond just translation. They're vital for optimizing the code, making it run faster, use less memory. They also expertly manage memory allocation, and crucially, they catch those errors early in the development cycle, before they become bigger problems.
And modern compilers are particularly good at this.
Oh, yes. Modern compilers are incredibly sophisticated. They significantly boost performance through advanced optimizations, things like loop unrolling, which sort of restructures loops to reduce overhead, or register allocation, which intelligently puts variables in the fastest possible memory spots right on the CPU. This makes them absolutely indispensable for building reliable, fast software, and software that can run on different types of computers, different platforms.
That's a really important point about portability.
Yeah.
Okay, so it sounds like compilers aren't just one single thing. They come in different flavors, right?
Yeah.
I've heard terms like single pass, multi-pass, load and go, debugging, and optimizing compilers. Could you give us a quick rundown? What do these categories mean for how a compiler works?
Sure. Each type is really tailored for a specific purpose or uses a distinct strategy. Let's break them down. First, single-pass compilers. They process the entire source code in, just one go.
So they're fast.
Very fast, relatively speaking, because they don't need to reread the code. But that speed comes at a cost. It often limits their ability to perform really complex optimizations. Then you have multi-pass compilers. These analyze the source code in multiple stages or passes.
Okay, so they take more time.
They do take longer to compile, yes. But this allows them to build up a much more complete understanding of the program's structure, and that enables much more aggressive and usually more effective optimizations. Better performance in the final program.
Makes sense. What about load and go?
Load and go compilers are kind of designed for immediate action. They compile the code and then immediately load and run it. You often see these in educational settings, maybe, where quick feedback is more important than squeezing out every last bit of performance.
Right, like for learning programming.
Exactly. Then there are debugging compilers. These are engineered specifically to help developers find bugs. They might insert extra code or metadata into the compiled program. This makes it easier to step through the code line by line in a debugger and see what's happening. The trade-off is usually that the resulting program runs a bit slower.
Okay, sacrificing speed for insight during development.
Precisely. And finally, optimizing compilers. These are, as the name suggests, laser-focused on generating the most efficient code possible. They use really sophisticated algorithms to minimize execution time, memory usage, everything. They almost always fall into the multi-pass category to achieve these deep optimizations.
So this raises an important question. How do these different types impact a developer's workflow or the final software performance?
Well, it's all about trade-offs, isn't it? If you need to compile very quickly, maybe during rapid prototyping, a single pass might be okay. If you're building a complex application where runtime speed is critical, you'll definitely want a multi-pass optimizing compiler. And during development, you might use a debugging compiler to track down issues, then switch to an optimizing one for the final release. The choice really depends on the project's priorities.
That clarifies the different approaches nicely. Now, regardless of the specific type, I understand there's a fundamental model of compilation they all sort of follow. It has two main blocks, analysis and synthesis. What actually happens in these two big phases?
That's right. Those two blocks, analysis and synthesis, represent the core sort of division of labor within the compiler. Analysis is the compiler's understanding phase. Think of it like the compiler reading your source code. It breaks down the raw text, which starts as just a stream of characters, into meaningful pieces. It figures out the structure. This process builds an intermediate representation of the code, often something like a hierarchical syntax tree.
Like diagramming a sentence in school.
Exactly like that. It's analyzing the code to understand its components, its grammar, how everything fits together. Then comes synthesis. This is the compiler's building phase. It takes the output from the analysis phase, that understood structured representation, and actually constructs the target program.
So it builds the new version in the target language.
Precisely. If analysis is understanding the original message, synthesis is writing that message anew in the target format, whether that's machine code or maybe in another high-level language. It's constructing the final output.
That translation analogy really helps. Okay, so within this big analysis synthesis model, there are even more specific steps. The phases of compiler. You mentioned 6 distinct phases, plus something called the symbol table. The source code goes through these one by one.
Yes, think of it like an assembly line. Each phase takes the output of the previous one, refines it, and passes it along. It's a pipeline. Let's walk through them.
Okay, phase 1.
Phase 1, lexical analysis. This is the very first steps, sometimes called the scanner or tokenizer. It scans the raw source code character by character and groups them into meaningful units called tokens.
Tokens, like words in a sentence.
Exactly. If you have int x equals 5, the lexical analyzer turns that into tokens like int, keyword, x, identifier, assignment operator, 5, integer literal, and end statement. It's where the raw text starts to get some structure.
Got it. What's next?
Phase 2. Syntax analysis, also known as parsing. This phase takes that stream of tokens from the lexer. Its main job is to check if the sequence of tokens follows the grammatical rules of the programming language. It builds a parse tree or syntax tree representing the structure.
So this is where it catches things like missing semicolons or mismatched parentheses.
Precisely. It ensures the code is structurally sound according to the language's grammar. If the syntax is wrong, it reports errors.
Okay, structure checked. Phase 3.
Phase 3. Semantic analysis. Now that we know the structure is correct, this phase checks if it actually makes sense. It ensures the code doesn't defy the rules of language in terms of meaning.
Meaning, like type checking.
Exactly. Type checking is a big part of it. If you try to add, say, a string variable to an integer variable in a language where that's not allowed, semantic analysis catches that. It tracks identifiers, checks their types, ensures everything is used correctly according to its definition. It's about logical correctness.
Okay, structure and meaning are validated. What now?
Phase 4. Intermediate code generator. After the analysis phases have understood the program's structure and meaning, the compiler generates an intermediate code, or IR. This isn't the final machine code yet. It's an abstract, machine-independent representation. Think of it as a halfway point.
Why have this intermediate step?
It's crucial for portability and optimization. Because it's machine-independent, you can apply optimizations here that work across different computer types, and it makes it easier to target different machines later.
Ah, okay. Which leads us to
Phase 5. Code optimization. This is where the compiler gets clever. It takes that intermediate code and tries to improve it. It looks for ways to make the program run faster, use less memory, or both. It might remove redundant code, rearrange instructions, simplify calculations, all sorts of tricks to make the code lean and fast.
like taking out unnecessary steps.
Exactly. Removing garbage code lines, as the outline puts it, maybe rearranging statements for better flow.
And the final phase.
Phase 6. Code generator. This is the grand finale. It takes the optimized intermediate code and it translates that IR into the specific machine language of the target computer. This produces the actual locatable machine code, the binary instructions the processor can finally execute.
The actual runnable program.
That's the one. And throughout all these phases, there's one more critical component, the symbol table.
Right, you mentioned that. What does it do?
Think of it as the compiler's memory or notebook. It's a data structure that stores information about all the identifiers used in the program, variable names, function names, constants, their types, their scope, where they are valid, and other attributes. Every time the compiler encounters an identifier, it checks the symbol table. When it finds a definition, it adds it to the table. It's constantly referenced and updated throughout all 6 phases.
So it keeps track of everything.
Everything important. It's essential for semantic analysis, for making sure variables are declared before use, for type checking, and even for code generation. If we connect this to the bigger picture, you can see how each of these steps is absolutely vital for producing a correct and efficient program. It's a complex but logical flow from human idea to machine action.
That's an incredibly clear breakdown of the core phases. It really shows the step-by-step transformation. But you mentioned that the compiler doesn't work in isolation. There's a supporting cast, these cousins of compiler and construction tools. Let's talk about the cousins first. 4 types: preprocessors, assemblers, loaders, and link editors, and 2-pass assembly. What roles do they play?
Right. These cousins are often essential parts of the overall process of getting a program from source code to execution, working alongside the compiler. First up, preprocessors. Think of these as a preparatory stage. They process the source code before the actual compiler even sees it.
What kind of preparation?
Several things. Macro processing is a big one. It lets you define short names or macros for longer pieces of code. The preprocessor just substitutes the long code wherever the short name appears. Then there's file inclusion, very common in languages like C or C++ way. You use directives like #include stdio.h. The preprocessor literally goes and fetches the content of that stdio.h file and pastes it into your code.
Ah, so that's how libraries get pulled in.
That's a key part of it, yes. There are also rational preprocessors, which can augment older languages with more modern features, like better control flow or data structures without changing the core compiler. And language extensions, where preprocessors add new capabilities through built-in macros. Essentially, they tidy up, expand, and prepare the code for the main compiler.
Okay, makes sense. What about assemblers?
Assemblers handle the translation from assembly language to machine code. Assembly language uses mnemonic names for machine instructions and symbolic names for memory locations, making it slightly more human-readable than raw binary. So instead of writing 011010111 000100010, a programmer might write MOVX R1. The assembler turns MOVX R1 into the correct binary sequence.
So it's a lower level translation than the main compiler does.
Exactly. It's usually the step after a compiler has generated assembly code, or sometimes programmers write directly in assembly. It converts those symbolic instructions, like MOV for move, ADD for add, into the actual machine instructions the CPU understands.
Got it. Then loaders and link editors. Sounds like they handle the final steps.
They do. They're crucial for getting the program ready to run. A loader takes the final machine code, often called relocatable machine code, and loads it into the computer's main memory so the CPU can execute it. It handles placing the code at the right memory address. A link editor, or often just linker, has a different job. Modern programs are often built from multiple source files, compiled separately into object files.
Right, large project.
Exactly. The linker takes all these separate pieces of compiled code and combines them into a single, final, executable program. It resolves references between the files, like if code in file A calls a function defined in file B, the linker makes sure that connection works.
It stitches everything together.
Precisely.
Yeah.
And finally, 2-pass assembly. This isn't a separate tool, but a common strategy used by assemblers. They sometimes need to read through the assembly code twice.
Why twice?
Well, in pass 1, the assembler scans the code primarily to find all the symbols like labels for jump targets or variable names and figure out their memory addresses. It stores this information in a symbol table. This handles cases where you might use a label before it's actually defined later in the code. Then, in pass 2, the assembler goes through the code again. Now that it knows the addresses of all symbols, thanks to pass 1, it can translate all the instructions into actual binary machine code.
The first pass builds the map. The second pass uses it.
You got it. What's fascinating here is how these components illustrate the modularity required in complex software systems. Each part does its specialized job.
It really is an ecosystem. Okay, so those are the cousins. What about the construction tools? These sound like tools used to build the compilers themselves. 5 types here: parser generators, scanner generators, syntax-directed translation engines, automatic code generators, and data flow engines.
That's right. Building a compiler is a complex task, and these tools help automate significant parts of it, making compiler development more manageable and reliable. Parser generators. These automatically create the syntax analyzer, the parser. You feed them a formal description of the language's grammar, like a CFG, and they generate the code that implements the parsing logic. Tools like Yak or Bison are famous examples.
Saves a huge amount of manual coding.
Immense amounts. Writing parsers by hand, especially for complex languages, is notoriously difficult and error-prone. Similarly, scanner generators. These automatically create the lexical analyzer, the scanner or tokenizer. You provide patterns, usually as regular expressions, that define what tokens look like. Keywords, identifiers, operators, etc. And tools like lex or flex generate the standard code.
Automating the first two phases, basically.
A large part of them, yes. Then there are syntax-directed translation engines. These help bridge the gap between parsing and later phases. They allow you to define actions, like building parts of an AST or performing semantic checks that should happen when the parser recognizes certain grammatical structures. Automatic code generators. These tools help automate the final code generation phase. They often work with pattern matching, taking intermediate code structures and generating the corresponding machine instructions based on a collection of rules for the target architecture. And finally, data flow engines. These are crucial for the optimization phase. They perform complex analyses to understand how data values flow through the program, where variables are defined, where they're used, how they might change. This information is vital for optimizers to figure out where and how they can safely improve the code.
So these tools essentially build the builders. They automate the hard parts of creating a compiler.
Exactly. They leverage theoretical computer science concepts to make practical compiler development feasible for complex modern languages.
Brilliant. We've got the big picture, the phases, the helpers, the tools. Let's circle back now and dive deeper into that very first phase again. Lexical analysis. You said it converts a sequence of characters into a sequence of tokens. Could you elaborate on this overview? What's really happening in this initial scan?
Absolutely. Lexical analysis performed by the lexer or scanner is that critical first contact the compiler has with your raw source guide. It's often tightly coupled with the parser, which handles the syntax analysis that follows. You see this pairing not just in compilers, but as mentioned in things like web browsers parsing HTML.
Right.
The core idea is taking that undifferentiated stream of characters, your program file, and breaking it into meaningful words or symbols, the tokens. Think of reading a sentence. Your brain automatically groups letters into words and recognizes punctuation. The lexer does the analogous thing for code.
And its applications go beyond compilers.
Oh, yes. While it's famously the first phase of a compiler's front end, often done in a single pass these days, lexers are also used in tools like pretty printers, software that formats code nicely, or linters that check for style issues or potential problems. Anywhere you need to break down raw text based on defined patterns.
How does the lexer actually work? You mentioned 2 stages.
Conceptually, yes. You can think of it in 2 steps. The scanner part reads the input and segments it into chunks, grouping characters that seem to belong together based on predefined rules. It identifies the boundaries of potential tokens. Then, the evaluator part takes these raw character chunks and converts them into a process value or token object, often associating a type, like keyword, identifier, operator, with the actual text, the lexeme. This structured token is what gets passed to the parser.
So the token itself is key. It's a structure holding the actual text, the lexeme, and its category. Here's where it gets really interesting. How does this seemingly simple line of code, say SUM 1 plus 2, in C actually get broken down into these tokens?
It's a great example because it's simple but shows the process clearly. Let's trace SUM 1 plus 2. The lexer scans S, then U, then M. It recognizes SUM as a sequence of letters, potentially an identifier, so it creates an identifier token with the lexeme SUM. Next, it knows this is the assignment operator, so an assign operator token with lexeme, then 1. It recognizes this as a number, an integer literal token with lexeme 1, then plus A, that's the addition operator, an add operator token lexeme path, then 2, another number, an integer literal token lexeme 2. Finally, as S, the end of statement marker, an end statement token, lexeme path, so that one line becomes a sequence of 6 distinct tokens, each categorized.
Wow. Okay, so it meticulously breaks it down piece by piece. What rules govern this? You mentioned lexical grammar.
Exactly. Every programming language has a lexical grammar or lexical syntax. These are the rules, often defined using mathematical formalisms called regular expressions, that specify what sequences of characters are valid for forming different kinds of lexemes. The lexer is essentially built to recognize strings that match these regular expressions and then produce the appropriate token category.
What about things like spaces or comments in the code?
Good question. Lexers typically recognize common categories like whitespace, spaces, tabs, newlines, and comments. Usually, once recognized, these are simply discarded by the lexer. They're important for human readability, but generally don't affect the program's execution logic, so the parser doesn't need to see them.
Usually. Yeah. Are there exceptions?
There are two vital exceptions where whitespace or comments do matter. One is in offside rule languages. Python is the most famous example. In Python, indentation, which is just whitespace at the start of a line, is used to define blocks of code, instead of using curly braces like in C or Java.
Ah, right. Indentation matters fundamentally in Python.
Critically. So for Python, the lexer must pay attention to indentation levels and generate special indentant tokens to signal block structure changes to the parser. Whitespace is syntactically significant. The other exception is when the lexer is being used for tasks where comments and whitespace need to be preserved, perhaps for a tool that analyzes comments or a code formatter that needs to maintain spacing.
That's a crucial distinction. So tokenization is this process of fixing boundaries, classifying segments, and passing tokens on. And you noted it's different from tokenization in computer security.
Yes, completely different meaning. In security, tokenization often refers to replacing sensitive data with non-sensitive equivalents called tokens. Here, in compiling, it's purely about breaking down the input stream into syntactically meaningful units for the parser.
Can you give a non-programming example of tokenization?
Sure. Think about natural language processing. Take the sentence. The quick brown fox jumps over the lazy dog. A tokenization process might break this down into individual words. The quick brown fox jumps over the lazy dog. You could represent this output in various ways. Maybe XML, sentence, word, quick word, sentence, or maybe an S expression common in Lisp, sentence, word via, word quick, word brown. The key is that the process takes a raw string and imposes structure by identifying and classifying the fundamental units, preparing it for deeper analysis, whether that's grammatical analysis of code or linguistic analysis of text.
Okay, the lexer has done its job. We have a stream of tokens. Now we hit syntax analysis, the second phase. You also called it parsing or hierarchical analysis. What's its main job here? Grouping tokens and checking grammar.
Precisely. Syntax analysis, or parsing, takes that sequence of tokens produced by the lexer and determines if they form a valid structure according to the programming language's grammar rules. If the sequence is syntactically correct, the parser's main output is a data structure that represents this grammatical structure, typically a parse tree, or, more commonly used in practice, an abstract syntax tree, AST.
So it's building a tree representation of the code's structure.
Exactly. That's why it's sometimes called hierarchical analysis. It reveals the hierarchical relationships between different parts of the code based on the grammar, going back to an operator like addition plus. The syntax rules might say an addition expression needs two operands. The parser checks. Is there a valid expression token followed by a plus token followed by another valid expression token?
But it doesn't care what type those expressions are yet.
Not at this stage, no. That's the job of semantic analysis later. The parser is only concerned with the structure. Does it look like a valid addition according to the grammar? It doesn't yet check if adding, say, a string and a number is meaningful.
Okay, structure only. What are the main objectives of syntax analysis then?
There are a few key goals. First, obviously, verify syntactic correctness. Does the code follow the language's grammatical rules? Second, if it is correct, construct a parse tree, or AST. This tree is the input for the next phases. Third, if it's not correct, report syntax errors meaningfully. Tell the programmer where the error is and, ideally, what kind of error it seems to be. And fourth, generally, prepare for semantic analysis and intermediate code generation by providing that structured representation, the AST.
And the way these grammatical rules are formally defined is using context-free grammar, CFG.
Yes, CFG is the standard formalism used to specify the syntax of most programming languages. It provides a precise mathematical way to define what constitutes a valid sequence of tokens.
What are the components of a CFG?
A CFG has four main parts. One, terminals. These are the basic symbols, essentially the tokens produced by the lexer. Things like keywords, if, while, operators, plus identifiers, x, my var, literals, 5, hello. They are the leaves of the parse tree. 2. Non-terminals. These represent syntactic categories or groupings of terminals and other non-terminals. Think of concepts like expression, statement, declaration. They are the internal nodes of the parse tree. 3. Production rules. These are the core of the grammar. They define how non-terminals can be constructed from sequences of terminals and other non-terminals. A rule like statement, if expression statement, defines one way to form a statement. 4. Start symbol. This is a special non-terminal that represents the highest level structure, usually the entire program, like program or compilation unit. Parsing starts by trying to derive the input token stream from this start symbol using the production rules.
Can you give a simple example for something like arithmetic expressions?
Sure. A common simplified CFG for arithmetic expressions might look like this. E.E plus TE a PT. An expression E can be an E plus a term T, or E minus T, or just a T. TTFT, FF, HMT can be T times a factor F, or T divided by F, or just an F. FEE, a factor F can be an expression in parentheses or an identifier ID. These rules capture how expressions are built and also implicitly handle operator precedence. Multiplication binds tighter than addition here.
That clarifies how the rules define structure. So given a CFG, how does the parser actually apply these rules? What are the main parsing techniques? You mentioned top-down and bottom-up.
Right. Those are the two main families of parsing algorithms. Top-down parsing starts with the grammar start symbol and tries to expand it using the production rules to eventually match the input token stream. It's like trying to predict the sentence structure from the top. Recursive descent parsing is a common top-down method. You basically write a function for each non-terminal in the grammar. When a function for non-terminal x is called, it looks at the input tokens and decides which production rule for x to apply, potentially calling other functions recursively. It's intuitive, but requires grammars without certain properties like left recursion. Predictive parsing, LL parsing, is a more optimized form of top-down parsing. It uses a look-ahead mechanism, looking at the next k input tokens, usually k1, to unambiguously decide which production rule to use at each step, avoiding trial and error backtracking.
Okay, so top-down starts from the goal, the start symbol, and works down. What about bottom-up?
Bottom-up parsing works the other way around. It starts with the input tokens, the leaves of the eventual parse tree, and tries to group them together using the production rules in reverse, eventually reducing the entire input sequence back to the start symbol. It builds the tree from the bottom up. Shift-reduce parsing is the general strategy for bottom-up. It uses a stack. It shifts input tokens onto the stack one by one. When the sequence of symbols on top of the stack matches the right-hand side of a production rule, it reduces them by replacing them with a non-terminal on the left-hand side of that rule. LR parsing is a very powerful and widely used family of shift-reduce techniques. L means scanning left to right. R means constructing a rightmost derivation in reverse. Tools like Yak and Bison generate LR parsers. They use pre-computed parsing tables, action and goto tables, and a stack to make parsing decisions very efficiently. There are variations like SLR, LALR, and CLR, differing in power and table size.
This raises an important question. Why are there so many different parsing techniques, and what are their trade-offs?
Good question. It boils down to a few things. Some techniques, like recursive descent, are easier for humans to write and understand, but they work only for a limited class of grammars. Others, like LR parsing, are more powerful and can handle a much wider range of grammars, but the parsing tables are complex and usually generated by tools. There are also trade-offs in terms of efficiency, how fast they parse, and how well they handle errors. The choice often depends on the complexity of the language being parsed and the requirements of the compiler.
Speaking of errors, syntax error handling is crucial for parsers. They need to not just detect errors, but report them effectively and maybe even try to recover, right?
Absolutely. A parser that just stops dead at the first error isn't very helpful. Good error handling aims to 1. Report errors clearly and accurately. 2. Recover from the error so it can continue parsing the rest of the file to find more potential errors in one go. Common recovery strategies include panic mode. As we mentioned, skipping input symbols until a known synchronizing token, like mobily, is found. Simple, but might miss errors in the skipped part. Phrase-level recovery. Making local corrections like inserting a missing token, for example a semicolon, or deleting an unexpected one. More complex but can yield better results, error productions. Adding explicit rules to the grammar that match common mistakes. Allows the parser to recognize the mistake and give a specific error message. Global correction. Trying to find the minimal set of changes to make the whole input valid. Very complex and rarely used in practice.
Okay, so after successful parsing and maybe some error recovery, the output is often an abstract syntax tree, AST. How is that different from a raw parse tree?
Right. A parse tree directly mirrors the derivation steps according to the grammar, including all the non-terminals and punctuation tokens. It can be quite cluttered. An abstract syntax tree, AST, is a more condensed, abstract representation. It captures the essential structural and semantic information of the code, but omits the extraneous details tied purely to the grammar rules, like parentheses used for grouping, or intermediate non-terminals that don't add meaning. For A plus BC, the AST would directly show the multiplication BC as a child node, which itself is a child of the addition node with A. It clearly reflects the intended operations and precedents, making it much better suited for subsequent phases like semantic analysis and code generation.
That makes sense. It's a cleaner representation. And finally, what parsing tools help automate this? You mentioned Yak Bison and LexFlex earlier.
Yes, those are the classic pairs. LexFlex, generate lexical analyzers, scanners. Yak Bison, generate parsers, typically LR parsers. Another very popular and powerful tool is ANTLR. Another tool for language recognition. It can generate lexers, parsers, often recursive descent, tree walkers, and works across many target programming languages. It's widely used for building compilers, interpreters, and other language processing tools. These tools take grammar specifications and automatically generate the complex parsing code, saving developers enormous effort.
Okay, we've got the tokens. We've parsed the structure into an AST. Now the compiler needs to check if it all makes sense. This brings us to type checking, a key part of semantic analysis. Its core job is ensuring the program follows the language's type compatibility rules.
Right.
Most languages need you to declare types before use.
That's generally true, especially for statically typed languages. Type checking is where the compiler verifies that operations are performed on compatible types of data. You can't, for example, meaningfully multiply a customer record by a file name in most languages. Type checking prevents such nonsensical operations.
How should we think about types? Are there different ways to define them?
Yes, there are a few perspectives on what a type represents. One, denotational view. Here, a type is simply a set of possible values, its domain. The type integer denotes the set, naga2, naga2, naga1, no, no, nay. The type Boolean denotes the set, true, false. Two, constructive view. A type is either primitive, like int, float, bool, or it's a composite type built by applying a type constructor, like array, record, pointer, to simpler types. So you can construct array of integer or record containing string and integer. 3. Abstraction-based view. Here, a type is defined by its interface, the set of operations that can be performed on values of that type, along with their expected behavior, semantics. This is very common in object-oriented programming where classes or interfaces define types.
Interesting perspectives. Now, a crucial aspect is when this checking happens. You mentioned static versus dynamic typing.
Right. This is about the typing performance in programming languages, specifically when type rules are enforced. Statically typed languages. Type checking is performed primarily at compile time. Examples include C, C++, Java, C#, Haskell, Rust. The compiler analyzes the code and flags type errors before the program even runs. This catches many errors early. Dynamically typed languages. Type checking is performed primarily at runtime. Examples include Python, JavaScript, Ruby, Lisp, Perl. You might write code that looks fine, but a type error, like trying to add a number to none in Python, only occurs when that specific line is executed. This offers more flexibility, but shifts error detection later.
And what about strongly typed versus weakly typed?
That's another dimension, related but distinct. Strongly typed languages. These languages have stricter type rules and generally don't allow implicit conversions between unrelated types that might lead to errors or unpredictable behavior. They aim to guarantee programs won't suffer from type errors at runtime, though the definition can be debated. Haskell and ML are often cited as strongly typed. Java is also generally considered strong. Weakly typed languages. These languages have more relaxed rules and might allow implicit conversions more freely, sometimes leading to unexpected results. C is often considered weakly typed in some aspects due to its handling of pointers and automatic coercions. JavaScript's type coercion rules are famously complex and sometimes surprising. And related to this is type-safe language. A language is type-safe if it prevents operations that violate the type system, ensuring you can't, for instance, treat an integer as if it were a memory address without explicit and potentially unsafe casting. Most modern managed languages aim for type safety.
So what does this all mean for you as a programmer?
It fundamentally dictates how and, crucially, when you'll find out about type-related mistakes. Static typing gives you early feedback during compilation errors or code before you run. Dynamic typing offers flexibility, maybe faster prototyping, but you need robust runtime testing to catch type errors that only manifest during execution. Strong typing generally leads to safer, more predictable programs, while weak typing might offer more low-level control or convenience at the cost of potential hidden errors.
Okay. How does a typical simple type checker within the compiler actually operate? You said it performs two main kinds of actions.
Yes, a basic type checker works closely with the symbol table and the AST. 1. Processing declarations. When it encounters a declaration, like int myvar or string name, it records the declared type information in the symbol table entry for that identifier. Myvar is an int, name is a string. 2. Checking expressions and statements. When it processes expressions like a plus b or statements like x, u, s, y, it retrieves the types of the involved identifiers and constants from the symbol table, or determines the type of literals directly. It then checks if the operation plus or is valid for those specific types according to the language's rules. If not, it reports a type error.
So these rules for declarations too?
Absolutely. The compiler uses a translation scheme, essentially, semantic rules associated with the grammar productions to handle declarations. For example, when it sees an array declaration like int scores 10, it needs to store not just that scores is an array, but also its element type, int, and its bounds, 0 to 9 typically. The type checker might store pointers to symbol table entries representing the lower, low, and upper high bounds, and the standard element type, integer, real, etc. Even scalar types might have these attributes internally, often set to NUL, for consistency in the type checking logic. There are functions like change to array internally that formalize this process of constructing array types from base types and bounds.
So it's meticulously tracking and validating types based on declarations and usage throughout the code.
Precisely. It ensures consistency and prevents operations on incompatible data.
All right, so types are checked, meaning it's validated. The compiler now moves to intermediate code generation, ICG. This sounds like a really pivotal phase, acting as a bridge between analysis and the final steps. You mentioned the intermediate representation, IR, generated here is designed to be machine independent. Why is that independence such a big deal?
It's hugely important for several reasons, making modern compilers much more effective and versatile. First, it provides an abstraction layer. Instead of needing a separate translator from, say, Java directly to by86 machine code, and another from Java to IR, and another to RISCV, you just translate Java to a common IR.
And then translate the IR to each machine.
Exactly. That significantly reduces the number of translators needed. It decouples the language-specific front-end from the machine-specific back-end. Second, it enables machine-independent optimizations. Many powerful optimizations, like identifying dead code or moving invariant computations out of loops, don't depend on the specifics of the target machine. You can perform these optimizations once on the IR, benefiting all target architectures. Third, it smooths code generation for different architectures. Having a well-defined IR means that when a new processor architecture comes out, you mainly just need to write a new backend that translates the existing IR to the new machine code. You don't have to rewrite the entire compiler front end.
That modularity sounds incredibly efficient. What are the main types of intermediate representations, IR, that compilers use?
They generally fall along a spectrum of abstraction levels. High-level IR. These are closer to the source language structure. They retain a lot of the original syntactic and semantic information. Abstract syntax trees, ASTs themselves, are often considered a high-level IR. They're good for high-level analysis and transformations. Low-level IR. These are much closer to the target machine language, often resembling assembly code, but they are still technically machine-independent, or use a generic machine model. They expose details like registers and memory addresses, often virtual ones. LLVM IR is a famous example, excellent for detailed, low-level optimizations. Medium-level IR. These strike a balance between high and low level. They abstract away some machine details, but are simpler and more linear than ASTs. 3-address code. TAC is the classic example here. It's widely used because it's relatively easy to generate from ASTs and suitable for many standard optimizations.
Okay, let's focus on 3-address code, TAC then, as seems common. What does it actually look like? What kinds of instructions does it use?
TAC is designed to be simple. Each instruction typically involves at most 3 addresses, hence the name, which could be variable names, constants, or compiler-generated temporary variables. Common TAC instructions include things like assignment, like x, y, op, z, e.g. t1 equals b plus c. Perform as a binary operation. Copy, like x, y, e.g. a equals t1. Assigns one value to another. Unary operations, like x equals opy, e.g. t2 equals meta is z. Operates on a single operand. Conditional jumps, Like if X relope, Y go to L, e.g. if I10 go to loop start. Jumps to label L if the condition is true. Unconditional jumps, like go to L, always jumps to label L function calls. Instructions for calling functions, call func N, and handling parameters return values, return statements, like return X.
Can you show how simple expression like AAB plus CD would look in TAC?
Sure. The compiler would break it down, typically introducing temporary variables, often denoted T1, T2, etc. T1 equals CD. Calculate the multiplication first due to precedence. T2 equals B plus T1, then perform the addition using the temporary result A equals T2, finally assign the result to A1. You see how each instruction is very simple, involving at most one operation and 3 addresses, CD, T1 in the first line. This makes it easy to analyze and manipulate.
That's very clear. And we also mentioned abstract syntax trees, ASTs, as a higher level IR. How does that represent the same expression?
The AST for A equals B plus CD would be a tree structure. The root node would be the assignment. Its left child would be the identifier A. Its right child would be the node for plus A. The plus node would have B as its left child. Its right child would be the node for A. And the node would have C and D as its children. So the tree structure directly reflects the operator precedence and the relationships between the operands, unlike the linear sequence of TAC.
Okay, different ways to represent the structure in operations. What about representing the program's flow, like branches and loops? That's where control flow graph, CFG, comes in.
Exactly. While TAC, or ASTs, represent individual computations, a control flow graph, CFG, represents the overall execution flow of the program. It's essential for many optimizations. A CFG consists of nodes. These represent basic blocks. A basic block is a sequence of consecutive instructions where a control flow enters only at the beginning and leaves only at the end without any jumps in or out in the middle. Think of it as a straight line piece of code. Edges. These are directed arrows connecting the basic blocks, showing the possible paths of execution. An edge from block A to block B means that after executing the last instruction of A, the program might next execute the first instruction of B.
Can you visualize that for something like an if statement?
Sure. Consider if block T, block F, block M. The CFG would show a basic block for the condition. There would be an edge from this block to block T, the true branch, and another edge to block F, the false branch. Then there would be edges from both block T and block F leading to block M, the block that executes after the if-else structure. This graph visually maps out all possible execution paths through that conditional logic, which is incredibly useful for analysis.
What's fascinating here is how these visual or structured representations help compilers understand the program's logic beyond just its syntax.
That visual clarity seems powerful. There's one more IR form you mentioned, static single assignment form, SSA. It sounds unique, each variable assigned only once. How does that help? SSA form is a specific type of IR where, indeed, every variable is assigned a value exactly once in the program text. If a variable in the original code is assigned multiple times, it gets renamed into different versions in SSA. This property makes many analyses and optimizations significantly simpler and more effective. For example, tracking how values propagate through the code, data flow analysis, becomes much easier because you know a variable's value is fixed after its single assignment point.
How do you convert code into SSA, especially with branches where a variable might come from different paths?
That's where the magic happens. 2 key things are needed. 1, variable renaming. As mentioned, each time a variable is assigned, it gets a new unique name, often with a subscript, like 1 by 2. Fee functions, this is the clever part. At points where control flow merges, like after an if-else statement, special functions are inserted. A fifth function takes multiple versions of a variable, one from each incoming path, and selects a correct one based on which path was actually taken during execution. For example, if by 1 is defined on the true path and by 2 on the false path, at the merge point you might have by 3 equals 1 by 2. By 3 then holds the value of either by 1 or by 2, depending on the execution flow, and by 3 is the single variable used after the merge.
That sounds complex but powerful for analysis. So once you have this optimized IR like TAC, SSA, or LLVM IR, how does code generation from IR actually happen?
This is the backend's job. It takes the optimized IR and translates it into the target machine's native instruction set. This involves several steps. Instruction mapping. Mapping the abstract IR instructions to concrete machine instructions. Often, one IR instruction might become several machine instructions. Register allocation. Assigning the program's variables and temporary values to the limited number of physical registers available on the CPU, trying to keep frequently used values in registers for speed. Instruction scheduling. Reordering the generated machine instructions to optimize for the target processor's specific architecture, like its pipeline depth, to maximize performance.
And what are the main tools for ICG used today?
Several major compiler infrastructures have well-defined IRs and tools around them, LLVM IR. As mentioned, used by the LLVM infrastructure, Clang, Swift, Rust, and X backend. It's a well-documented, low-level SSA-based IR designed for powerful optimization and retargeting. Gimple and RTL, GCC. The JNU compiler collection, GCC, uses its own internal representations. Gimple is a simpler, tuple-based representation derived from the initial ASTs, and RTL, Register Transfer Language, is a lower-level representation closer to machine instructions used for machine-specific optimizations. JVM bytecode. The intermediate representation for Java and other JVM languages, Scala, Kotlin, it's executed by the Java virtual machine, making Java code portable. It's a stack-based bytecode format. These IRs and the toolchains built around them are absolutely central to modern compiler technology.
We follow the journey through analysis and intermediate representations. Now we arrive at the final crucial phase, code generation. This is where the optimized intermediate value finally gets mapped to the target machine's language, producing that locatable machine code. You mentioned sophisticated compilers might do this in multiple passes too. Why would they do that, and how does it help with supporting different computer architectures?
Yes, even the final code generation might involve multiple stages or passes, especially in highly optimizing compilers. One reason is that some optimizations are best performed very late, on a representation that's quite close to the final machine code. For instance, detailed instruction scheduling really needs to know the exact latencies of machine instructions. Also, breaking it down allows for better separation of concerns. You might have a pass focused purely on register allocation, followed by a pass focused on scheduling. The multi-stage approach greatly helps with targeting multiple architectures. The earlier phases, front-end parsing, semantic analysis, generating a common IR, and machine-independent optimizations can be shared across all targets. Only the final stages, which translate the low-level IR into specific machine code for, say, x86 versus ARM versus MIPS, need to be different. This modularity, this retargetability, is a huge win.
So it makes the compiler much more adaptable. What's the typical input to this final code generation phase?
The input is typically the optimized intermediate representation, often something like 3-address code, SSA form, or a low-level IR like LLVM IR or GCC's RTL. This IR has already been processed and improved by the middle-end optimizer.
And what are the main tasks of code generation that need to happen now? You listed 3 key ones.
Right. The final code generator has 3 critical responsibilities. 1. Instruction selection. This is choosing the actual machine instructions that will implement each IR operation. A target machine might have multiple ways to do the same thing. Example, different addressing modes for memory access or specialized instructions. The code generator needs to pick the best sequence, considering speed and code size. 2. Instruction scheduling. After selecting the instructions, it needs to decide the exact order in which they will appear in the final code. On modern processors with complex pipelines and parallel execution units, the order can significantly impact performance. Good scheduling avoids stalls and maximizes throughput. 3. Register allocation. This is assigning program variables and temporary values generated by the compiler to the processor's physical registers. Registers are the fastest memory available, so keeping frequently used data in registers is critical for speed. But there are usually only a small number of registers, so this is a complex allocation problem deciding which variables live in registers at which points in the code.
That sounds like a tricky balancing act, especially register allocation. You also mentioned instruction selection stages. Can you elaborate on that?
We can think of instruction selection happening in conceptually 2 stages as the code transforms. First, there's the conversion from the higher level representation, like an AST, into the linear lower level intermediate code, like TAC. This is a form of instruction selection, choosing the appropriate IR instructions. Second, and what we usually mean by instruction selection in the backend, is the conversion of that low level IR into the actual target machine instructions. This often involves pattern matching, recognizing patterns in the IR that correspond to specific machine instructions or sequences of instructions. This phase might be relatively simple if the IR is very close to the machine language, or quite complex if significant translation is needed.
Okay. Now, there's a different approach too. Runtime code generation, or just-in-time JIT compilation. This sounds like code generation happens while the program is running.
Exactly. JIT compilation is a hybrid approach used in many modern language runtimes, like for Java, JVM Hotspot, .NET, CLR, and JavaScript, V8 Engine. Instead of compiling everything to native machine code before execution, ahead of time, or AOT compilation, a JIT compiler translates intermediate code like Java bytecode or JavaScript into native machine code during program execution, often on a method-by-method or even loop-by-loop basis.
Why do that? What are the benefits?
It offers a compelling blend of portability and performance. Portability. You can distribute the platform-independent intermediate code, like Java bytecode, and the JIT compiler on the user's machine handles the final translation to whatever specific CPU they have. Optimization opportunities. This is the really interesting part. A JIT compiler operates at runtime, so it can observe how the code is actually being used. It can gather profiling information, which methods are called most often, hotspots, which branches are usually taken.
So it can optimize based on real usage patterns?
Precisely. It can then apply highly aggressive optimizations specifically to those hotspots, potentially achieving better performance than an AOT compiler, which has to make assumptions about usage patterns. Even if the initial JIT compiled code is less optimized, the ability to re-optimize critical sections based on runtime data is very powerful.
That's fascinating. So it adapts the optimization strategy dynamically.
Yes. If we connect this to the bigger picture, JIT compilation is a powerful illustration of how performance can be optimized even during execution, adapting to real-world usage in a way that static compilation cannot. It's a key technology behind the performance of many modern dynamic languages and managed runtimes.
That dynamic aspect of JIT is really cool. Okay, whether it's AOT or JIT, a major goal is performance. Let's focus now on code optimization itself. This is about transforming the program to run faster and use fewer resources, right? Replacing high-level constructs with more efficient low-level code.
Exactly. Code optimization is a phase, or often multiple phases, within the compiler dedicated purely to improving the generated code without changing its functional behavior. The goal is to produce a program that achieves the same result but is faster, smaller, or uses less power.
What are the ground rules for optimization? The compiler can't just change things arbitrarily, can it?
Absolutely not. There are crucial rules. 1. Preserve meaning, the most important rule. The optimized code must produce the exact same output and have the exact same observable side effects as the original code for all valid inputs. Optimization must not introduce bugs. 2. Improve performance, reduce resources. The optimization should actually make the program faster or use less memory power, etc. There's no point in an optimization that makes things worse. 3. Be worth the cost. The time taken to perform the optimization during compilation should be reasonable. A very complex optimization that saves milliseconds at runtime but adds minutes to compile time might not always be desirable, especially during development. So optimization itself should be reasonably fast.
Where do these optimization efforts happen?
Optimization can occur at multiple levels. Source code level. Programmers themselves can optimize by choosing better algorithms or data structures. This often yields the biggest gains. Intermediate code level. This is where most machine-independent optimizations happen. The compiler works on the IR, like TAC or SSA, to improve logic, simplify expressions, optimize loops, etc. Target code level. Machine-dependent optimizations occur here after or during the generation of machine code. This involves leveraging specific features of the target CPU, like its instruction set, registers, and cache hierarchy.
You mentioned machine-independent and machine-dependent optimization. Can you elaborate on those types?
Sure. Machine-independent optimization. These transformations are applied to the intermediate representation and don't rely on any specifics of the target hardware, CPU architecture, number of registers, cache size. They improve the code based on its logical structure. Examples include constant folding, calculating expressions like 3 plus 5 at compile time, replacing it with 8, dead code elimination, removing code that can never be reached or whose result is never used. Loop invariant code motion, moving calculations out of loops if they produce the same result in every iteration. Common subexpression elimination, calculating a repeated expression once and reusing the result. Machine-dependent optimization. These optimizations do rely on the specifics of the target machine. They happen later in the compilation process, often during or after final code generation. Examples include register allocation, intelligently assigning variables to the machine's registers, instruction scheduling, reordering instructions to best suit the CPU's pipeline, using specialized instructions, employing specific hardware instructions for tasks like vector operations, SIMD, cache optimization, arranging code or data access patterns to make better use of the CPU cache.
That distinction makes sense. And you highlighted loop optimization as particularly important. Why loops?
Because programs spend a huge proportion of their execution time inside loops. Think about processing data sets, iterating through game updates, handling network requests. Loops are everywhere. Even a small percentage improvement in the speed of a frequently executed loop can lead to significant overall performance gains.
So, what are some common techniques for optimizing loops?
Compilers have a whole arsenal of loop optimization techniques. Loop invariant code motion. As mentioned, identifying calculations inside a loop whose results don't change from one iteration to the next and moving them before the loop starts. This is one of the most effective loop optimizations: induction variable analysis and strength reduction. This involves analyzing variables that change predictably within a loop, like loop counters. Often, calculations involving these variables can be simplified. For example, if you have j equals I4 inside a loop where it increments by 1 each time, you can potentially replace the multiplication with a cheaper addition j equals j plus 4, strength reduction, using the value of j from the previous iteration. Loop unrolling. Replacing a loop body with several copies of itself, adjusting index variables accordingly, and reducing the number of loop iterations. This reduces the overhead of the loop control, checking the condition, jumping back, and can expose more opportunities for other optimizations, like instruction scheduling. Loop fusion fission. Combining adjacent loops that iterate over the same range, fusion, or splitting a single loop into multiple loops, fission, can sometimes improve cache locality or enable other optimizations.
Here's where it gets really interesting. Even tiny changes in a loop can have massive impacts on performance, highlighting the power of these optimization techniques.
Absolutely. Optimizing compilers spend a lot of effort analyzing and transforming loops precisely because the payoff can be so large. It's a fascinating area where understanding both the code's logic and the target machine's characteristics is crucial.
We've seen how compilers optimize code for speed. Now let's shift focus to another critical resource: memory. Memory management is fundamental to how modern computers work, dealing with allocating, using, and freeing memory. How does it impact performance and stability?
Memory management is absolutely critical. It's the system responsible for orchestrating how programs use the computer's memory resources throughout their life cycle. Effective memory management is vital for performance. Getting data to the CPU quickly is key. Efficient allocation and locality, keeping related data close together, improve cache performance. Stability. Poor memory management leads to notorious problems like memory leaks, where unused memory is never freed, eventually exhausting resources, and fragmentation, where free memory is broken into small, unusable pieces. It can also cause crashes due to accessing invalid memory, like dangling pointers. Resource utilization. Ensuring that memory is used efficiently, allowing multiple programs to run concurrently without interfering with each other.
What are the main objectives of a memory management system?
The primary goals are to provide mechanisms for easy allocation and deallocation of memory as programs need it, to effectively maintain the different memory areas, primarily the stack for function calls and the heap for dynamic data, to actively work to reduce memory leaks and fragmentation, and fundamentally to enable multitasking and virtualization by securely and efficiently sharing the finite physical memory among competing processes or virtual machines.
You mentioned performance being tied to getting data quickly. How does the memory hierarchy help with that?
The memory hierarchy is a core concept in computer architecture. It recognizes that there's a trade-off between memory speed, size, and cost. So systems use multiple levels of memory organized in hierarchy. Registers. Fastest, smallest, most expensive. Right inside the CPU. Hold currently active data. Cache memory, L1, L2, L3. Faster, smaller, more expensive than RAM. Sits between CPU and RAM. Holds recently or frequently accessed data from RAM to speed up access. Main memory. RAM, slower, larger, cheaper than cache, the main working memory for active programs and data. Volatile, data lost on, power off. Secondary storage, SSD, HDD, much slower, much larger, much cheaper than RAM. Non-volatile storage for files, applications, OS, sometimes, virtual memory. Uses secondary storage to simulate extra RAM, slowest level.
And data moves between these levels.
Yes, constantly. The memory management system, often in coordination with hardware, tries to keep the data the CPU is most likely to need soon in the fastest levels, registers and cache. When the CPU needs data not in the cache, it has to fetch it from RAM, cache miss, which is slower. If it's not even in RAM, page fault, using virtual memory, it has to be fetched from disk, which is much slower. Optimizing for this hierarchy is crucial for performance.
Okay, let's talk about how memory actually gets assigned to programs. What are the main memory allocation types? Static, stack, and heap.
These refer to when and where memory for program data is allocated. 1. Static memory allocation. This happens at compile time. The compiler determines the size and location of memory for certain variables before the program runs. This memory exists for the entire duration of the program,
Global variables and static local variables in CC++ are examples. It's simple and efficient, but inflexible to size must be known at compile time. 2. Stack memory allocation. This is used for managing memory related to function calls. When a function is called, a block of memory, a stack frame, is automatically allocated on the stack to hold its local variables, parameters, and return address. When the function returns, this memory is automatically deallocated. It's very fast and efficient due to its simple LIFO, last in, first out structure, but the total stack size is usually limited. 3. Heap memory allocation. This is for dynamic memory allocated during program execution, where the size or lifetime isn't known at compile time. Programmers explicitly request blocks of memory from the heap, even ample using malloc in C or new in C++ Java, and are often responsible for explicitly freeing it later, free or delete. The heap is flexible, allowing complex data structures to grow and shrink, but managing it correctly is harder, leading to risks like memory leaks or fragmentation, if not careful.
That distinction is really important. And different programming languages handle this quite differently, right? Tell us about memory management in programming languages.
Absolutely. The language itself often dictates the primary memory management model, CC++ stuff, famous for manual memory management. The programmer has direct control over heap allocation, malloc-free, new delete. This offers maximum performance potential, but puts the burden of correctness entirely on the programmer. Memory leaks and dangling pointers are common pitfalls. Java, Python, C#, JavaScript, and many others, these use automatic memory management primarily through garbage collection, GC. Developers typically create objects on the heap, new in Java, #, or implicitly in Python.js, but they don't explicitly deallocate them. The language runtime environment has a garbage collector that periodically identifies and reclaims memory occupied by objects that are no longer reachable by the program. Rust takes a unique approach with its ownership system. It achieves memory safety, preventing leaks and dangling pointers, without a traditional runtime garbage collector. It uses a set of compile time rules about variable ownership and borrowing to determine when memory can be safely freed. If the rules are violated, the code won't compile.
This raises an important question. How does a language's approach to memory management impact a developer's responsibilities and the potential for bugs?
It has a huge impact. In CC++ AMP, the developer must be meticulous about memory. Every malloc needs a corresponding free. The potential for bugs is high, but you have fine-grained control. In GC languages like Java or Python, the developer is freed from manual delocation, significantly reducing memory bugs, but they give up some control and might face occasional pauses when the GC runs. Rust tries to offer the best of both worlds, compile time safety guarantees like GC, but with the performance characteristics closer to manual management. The choice impacts development speed, potential bugs, and performance profiles.
Let's focus on garbage collection, GC, since it's so common in managed languages. How does it automatically find and recover unused memory? Are there different methods?
Yes. GC is a whole field of study, and various algorithms exist, each with pros and cons. Some major types or techniques include reference counting. The system keeps account of how many references point to each object on the heap. When an object's reference count drops to 0, it means nothing is pointing to it anymore, so it's garbage and can be immediately reclaimed. Simple and immediate, but traditionally struggles with circular references, where objects point to each other in a cycle, keeping their count 0 even if the whole cycle is unreachable. Mark and sweep. This is a common tracing algorithm. It works in 2 phases. First, the mark phase starts from known roots, like global variables in the current stack, and traverses all reachable objects, marking them as live. Second, the sweep phase scans the entire heap and reclaims the memory of all objects that were not marked because they are unreachable garbage. Generational GC. This popular technique is based on the observation that most objects die young. It divides the heap into generations, for example, young and old. New objects are allocated in the young generation, which is collected frequently and efficiently. Objects that survive multiple young collections are promoted to the old generation, which is collected less often. Compacting GC. Over time, allocating and freeing objects can lead to fragmentation. Compacting collectors not only free garbage, but also move the surviving objects together in memory, eliminating gaps and creating large contiguous blocks of free space. This improves allocation speed later, but adds the overhead of moving objects and updating pointers.
Lots of different strategies there. Okay, moving up a level, what about virtual memory and paging? These sound like operating system concepts that interact with memory management.
They are, and they're fundamental to how modern systems manage memory efficiently and securely. Virtual memory. This is a technique where the operating system makes the computer appear to have more main memory, RAM, than it physically does by using disk space as an overflow area.
Each program runs in its own private virtual address space, which is mapped by the OS and CPU hardware using page tables to actual physical RAM addresses or locations on disk, the swap file or paging file. This allows running larger programs than physical RAM allows and lets many programs run concurrently without interfering with each other's memory. Paging. This is the common mechanism used to implement virtual memory. Both physical RAM and the virtual address space are divided into fixed-size blocks called pages, for example, 4KB. The OS manages the mapping between virtual pages and physical page frames in RAM using page tables. When a program accesses a virtual address, the hardware translates it to a physical address. If the required page isn't currently in RAM, a page default, the OS needs to load it from disk, potentially swapping out another page from RAM to make room. Demand paging is the strategy of only loading pages from disk when they are actually accessed, not beforehand.
That explains how systems juggle memory. But what about memory fragmentation? That sounds like a problem that arises from all this allocation and deallocation.
It is a significant problem, especially for long-running programs or systems using manual memory management or non-compacting GCs. Fragmentation means that the free memory on the heap gets broken up into many small, non-contiguous blocks over time. Even if there's enough total free memory available, you might not be able to satisfy a request for a large contiguous block because no single free block is big enough. This leads to allocation failures or forces the system to do more work, like compaction. As mentioned, the compaction technique is used by some garbage collectors or memory managers to combat fragmentation. It rearranges memory, moving allocated objects together to consolidate the free space into larger chunks.
This has been an incredibly detailed look at compilers and memory. Let's turn to the final topic, error handling. Something every developer deals with daily. It's critical not just in compilers, but in all software, right? Ensuring systems can recover from the unexpected.
Absolutely. Error handling is a cornerstone of robust software engineering. Things will go wrong, invalid user input, network failures, file not found, programming mistakes. Good error handling ensures the system can detect these situations, respond appropriately, and ideally recover or at least fail gracefully rather than just crashing or producing incorrect results. It massively impacts reliability, maintainability, and the overall user experience.
What are the primary objectives of a good error handling strategy?
You want your error handling too. Detect and report errors clearly and easily. Make it obvious that an error occurred, what the error was, and ideally where it happened. Prevent system crashes or corruption. Errors shouldn't bring down the entire application or leave data in an inconsistent state. Provide relevant feedback to users or developers. Error messages should be informative. Facilitate debugging and troubleshooting. Good error information makes it much easier to find and fix the underlying problem.
Okay, so what kind of errors are we talking about? The outline lists 6 types of errors. Can you break those down?
Sure. Errors can be classified based on when and why they occur. 1. Syntax errors. These are violations of the language's grammar rules. Caught by the compiler's parser. Example, intex equals 5, missing semicolon in C. The code structure is wrong. 2. Semantic errors. The code is grammatically correct but violates the language's meaning rules. Also caught by the compiler, semantic analysis phase. Example, x equals y plus 5, where variable y hasn't been declared, or trying in result hello plus 5 if the language doesn't allow adding strings and integers. It's structurally okay, but logically flawed according to language rules. 3. Runtime errors. These occur while the program is executing. The code compiled fine, but something goes wrong during execution. Examples, dividing by 0, trying to access an element outside array bounds, array index out of a bounds exception, trying to use a null reference, null pointer exception, often cause crashes if not handled with try-catch blocks or similar mechanisms. 4. Logical errors. These are bugs in the program's algorithm or logic. The program compiles and runs without crashing, but it produces the wrong output or behaves incorrectly because the programmer's logic was flawed. Example, using instead of in a loop condition leading to incorrect results. These are often the hardest to find because there is no explicit error message. 5. Compilation errors. This is a general term covering both syntax and semantic errors detected by the compiler. They prevent the compiler from producing an executable file. 6. Linking errors. These occur after individual source files have been compiled successfully, during the linking phase when the compiler tries to combine them into a single executable. Example, your code calls a function do something, but the linker can't find the compiled code for that function in any of the object files or libraries being linked. You get an undefined reference or unresolved external symbol error.
What's fascinating here is how these different error types highlight the various stages of a program's life cycle where things can go wrong, and how compilers act as vigilant gatekeepers for some types.
Exactly. Compilers have the first line of defense against syntax and semantic errors. Linkers catch integration issues. Runtime errors and logical errors require careful programming, testing, and often runtime error handling mechanisms within the code itself.
So, focusing back on the compiler, how does it handle error handling? We touched on recovery strategies and parsing, but what about reporting? How important are good error messages?
Error messages are incredibly important. A good error message should be clear and precise. State exactly what the problem is, locate it. Indicate the file name and line number, and maybe column where the error was detected. Informative. Give hints about the likely cause or how to fix it, if possible. A message like error on line 50 is nearly useless compared to error on line 50, type mismatch, cannot assign string to variable of type integer.
And the compiler uses strategies to try and find more than one error.
Yes, good compilers try to recover and continue after finding an error, using those techniques we discussed. Panic mode recovery. Skip input until a known synchronization point. Phrase level recovery. Make local corrections. Insert deleter place tokens. Error productions. Define grammar rules for common mistakes. Global correction. Rarely used. Find the minimal change to fix the input. The goal is to report as many genuine errors as possible in one compilation run to save the developer time.
Okay, so the compiler helps find compile time errors. But for runtime and logical errors, we need debugging techniques. What are the main tools and methods developers use?
Debugging is the art and science of finding and fixing bugs that manifest when the program runs. Key techniques include 1. Logging. Instrumenting your code to print out messages or variable values to a console or file during execution. Print statements are a simple form of logging. More sophisticated logging frameworks allow controlling levels of detail. Debug, info, error. Analyzing the logs helps trace execution flow and variable states leading up to an error. Example, import logging. Logging.error, file not found, file plus file name. 2. Debuggers. These are powerful tools like GDB, LLDB, Visual Studio Debugger, browser developer tools that let you interact with your program while it's running. You can set breakpoints to pause execution at specific lines. Step through code line by line, step over, step into, step out of functions. Inspect variables in memory to see their current values. Examine the call stack to see the sequence of function calls. Debuggers are essential for understanding complex runtime behavior and diagnosing crashes or logical errors. 3. Static code analysis. Using tools like SonarQube, Pylint, CheckStyle, linters that analyze your source code without running it. They can detect potential bugs, style issues, security vulnerabilities, and code smells based on patterns and predefined rules. This helps catch problems before they even become runtime errors.
So it's really a combination of compiler checks, runtime handling within the code, and these powerful debugging tools that help create reliable software.
Exactly. It's a collaborative effort between the compiler, the runtime environment, the programmer's diligence in writing error handling code, and the use of effective testing and debugging tools. #TAG outro.
Wow. What an incredible journey we've taken today. From just a simple line of code typed by a human, all the way down through lexical analysis, parsing, semantic checks, intermediate code, optimization, and finally, actual machine instructions. We've really unpacked how a compiler orchestrates this incredibly complex dance. It's truly a marvel of engineering that makes so much of our digital world possible.
It really is. There's so much hidden complexity beneath the surface of even the simplest program execution.
So what does this all mean for you, our listener? Well, hopefully it means appreciating the sheer ingenuity behind the software you use every day. And maybe, just maybe, understanding your own code or the tools you use just a little bit better, knowing the incredible transformation happening under the hood.
Indeed. And it's important to remember that compilers are far more than just simple translators. They are highly sophisticated, intelligent systems. They are constantly evolving, incorporating new research and optimization, new language features, new hardware capabilities, all to make software faster, more efficient, and more reliable. The principles we've discussed today really do shape the very fabric of modern computing.
That's a great way to put it.
And maybe a final thought for you to ponder. Consider how the rapid rise of AI-powered code generation tools might further blur these lines. The lines between high-level human intent and low-level machine execution. Could this change how we even define and interact with the concept of compilation in the future? It's certainly an interesting space to watch.
That is a fascinating thought to end on, the future of how we create software.
Thank you for joining us on this deep dive into the world of compilers.
Yes, thank you for listening to The Deep Dive.